Welcome to the lesson 13 of industrial instrumentations. We will continue with the flow meters. So, in the lesson 12 also we have seen the flow meters, because as I told you earlier that the flow, the variety of the flow, the variety of the instruments for measuring the process parameters like flow are the huge in number. So, what we have to do, we have to cover lot of sensors, unlike the temperatures and pressure level, very few number of sensors are available, but due to the varieties and the environment conditions, the number of flow meters are quite large in number. So, this lesson 13 also is for the flow meters. So, we have given the name flow meter 2. You see here the contents of this lesson is pitot tube, which is extensively used for not only for the flow measurements, also for the velocity measurements. Okay. If I can install, and it is basically mostly used for the, not for the liquid, but for the gas. Even for a high speed vehicles also I can use this for measurement of the speed of the vehicles by using the pitot tube. One of the common applications of the pitot tube is the aircraft speed measurements, where in a high altitude. So, there is a differential pressure, and another important thing, this pitot tube as well as the elbow meters, which is next you will find, is basically depends on the differential pressure measurements. We have seen that differential pressure measurement technique is utilized in the case of orifice meter and venturi meter. So, in pitot tube and elbow meter also we will see that we will use the same principle. That means there is a differential pressures, and that pressures is calibrated in terms of flow velocity or the volume flow rate. So, the contents are pitot tube, elbow meter, then rotameter is another example, but rotameter, as you know, it's not the differential pressure, it's not the flow meter, depends on the, based on the differential pressure measurements, it is basically variable area meter. So, that we will discuss in details how it works actually, and also we will solve one problem on the venturi meter. So, on the differential pressure meter, so either venturi and orifice. So, in this particular lessons we will consider one problem on the venturi meter, right. So, at the end of this lesson the viewer will know the principle of working of pitot tube, advantage and disadvantage of elbow meter, also its principle also we will learn in this process. So, principle is common, principle of working of pitot tube, elbow meter, your rotameters, everything will be, all will be discussed here, but also we will discuss advantage and disadvantage of the elbow meter. Also we will see that rotameter can be used as a linear sense, that is a great achievement, because in most of the differential pressure, in all differential pressure measurement based flow meter, you will find its relation between the flow and the differential pressure is non-linear. So, which creates a problem. So, we need some other circuitry to linearize, which is not necessary in the case of rotameter, though it is usually used for very short range of flow measurement, range is not much, right. So, pitot tube, you see it is like this. It measures the velocity at a point in a fluid, right. That means it will measure particularly velocity at a point, unlike the orifice meter and venturi meter, which measures over area. If you look at the along the pipe, if you go along the pipe. So, but the pitot tube is basically measure the velocity at a point, particular point in a fluid, right. So, this is very important. That means what I am saying here, you see, if I take a whiteboard, and that means what I am saying, that if I have a pipe, we have seen that in the case of orifice meter, okay, or if I have in the case of venturi meter, we have seen. So, it's average the velocity at the whole point, okay. It's like this one, it average the velocity. If I am interested by the pitot tube, if I interested to measure the velocity, suppose at this point of the fluid, or at this point of the fluid, or this point of the fluid, by this of the fluid, that is not possible in the by Venturi or orifice meter, right, but it is possible by the pitot tube. And another important thing is it is an open channel meter, it is not a closed. You can use it as a closed channel meter, but you can use it as well as open channel meter. That means I have a tube, what they actually will discuss in details. So, this tube is installed, okay, inside the pipe, suppose this is a pipe. So, depending on the installation, I can move it little up here in this, or I can move it down. So, I can at a particular point I can measure the velocity of the fluid, right. Like Weir's, this is also an open channel meter, but we can use it as a closed channel meter also. It measures the velocity at a point in a fluid. It is an open channel meter that I told you. It is suitable for investigation around an aerofoil in a wind tunnel or the measurement of velocity profile in a pipe prior to installation of the permanent flow meter. Sometimes some estimation is necessary, that means how much is the flow, I mean before installing your flow meters like Venturi meters or orifice meter or dull tube and flow nozzles. So, we need some estimation. So, in that type of situation, pitot tube is can be easily inserted and take the measurement, because you know that in the case of orifice meter, Venturi meter, it is a very cumbersome devices, it needs a lot of time, but for the estimation this not, you cannot spend that much of time, neither nobody will allow to disturb the installation, but in the by using the pitot tube you can overcome that type of difficulties, that I can estimate, as well as I can measure quite accurately the flow velocity or flow measurements. You can see there in the case of Venturi meter and orifice meter also, we are actually measuring the velocity, then we are multiplying the area of cross sections, finding the total volume flow rate. Here we will find the velocity, then with the area if you of the cross section of the pipe you multiply, obviously you will also get the volume flow rate. The principal operations of pitot tube is like this. If a solid body is held stationary in a pipe in which the fluid is flowing with a velocity as the fluid in the tube approaches the body, the fluid particles are decelerated, and until at a point directly in front of the solid body the velocity of the fluid is 0, right. What does it mean? Let us take a blank page, then it will be more clear. See here. So, what I am saying, suppose a fluid, I have a pipe and liquid is flowing through this, right. Now, I put an object, suppose like this one, a solid object, then what will happen? See here, the liquid will flow in this direction, flow in this direction, all this direction. What happened to the fluid which is coming to this, hitting this portion? It is coming to rest at that position, okay. Supposed to be there, if it is rest, the pressure will be very high compared to the pressure of the fluid here, right. So, that means the liquid which is coming to the rest in contact. So, liquid, so what will happen? The fluid will be decelerated. When it is coming approaching this solid body, suppose if I take this is a solid body, the fluid will be decelerated. So, at this point it will be totally stopped. So, velocity of the liquid at this point will be 0, exactly identically 0, and the velocity of the fluid, suppose this is V. So, this liquid also flowing the velocity V, then it is flowing out, again it is flowing out, right. But whenever the fluid is flowing here, so obviously the just in front of this one, if you look at here at this position, the fluid will come to rest. Using these principles actually people developed the pitot tube, right. Just take the, so again I will repeat, if a solid body is held stationary in a pipe in which the fluid is flowing with a velocity, as the velocity in the tube approaches body, the fluid, that solid body, obviously this is a pipe and the solid body, the fluid particles are decelerated until at a point directly in front of the solid body the velocity of the fluid is 0, velocity of the fluid is 0, right. So, accompanying the deceleration is an increase in pressure, right. That means, whenever I told you earlier also, that means what will happen? That means I have a solid body here, again I am telling, so liquid is coming and hitting here. So, velocity at this point is 0, right, velocity v it is flowing, right, this is the pipe is flowing. So, what will happen here? I will take a new page, okay. So, like this one, it is flowing like this, right. So, what will happen you see here? So, I have a solid body, so which is coming and coming to. So, the pressure at that point will be high compared to the, or highest I should say, compared to the fluid, I mean static pressure there, right. So, accompanying the deceleration is an increase in pressure. So, it is the process of converting the velocity head to an additional static head, right. We are calling it head because it is a basically if you look at is basically we are writing the equations in terms of the liquid head, right. So, that is the reason we are because any I mean if the pressure is as you know HdG, if you divide by density and the acceleration due to gravity. So, obviously, it will can be expressed in terms of only the height. That means, as you know the liquid the pressures is usually defined like this one, is not at P equal to height to d into g. So, if we expressed, if you multiply I mean divide by d and g, obviously I will get a, if I write the Bernoulli's equations only in the case of in the terms of height. So, it will be all in I mean head. So, that is the reason sometimes we call it head. It is the process of converting the velocity head to an additional static head, right, because additional static head is coming, velocity is becoming 0, the pressure is increasing. So, that is head is also increasing. The velocity of the fluid can be found by measuring the differential pressure, again the same principles, because this also depends on the basically the principle of working depends on the measurement of the differential pressure. At the impact hole or stagnation point, the fluid is brought to rest, and this point therefore has no kinetic energy, right. If the velocity is 0, obviously what is the kinetic energy? Half mv square. If the velocity is 0, the kinetic energy also will be 0, right. So, here you see the a pitot tube, look at very carefully, right. So, you see this is a pitot tube, our liquid is flowing, it is installed in a pipe. I have not shown the pipe. So, pipe will be there, right, pipe will be there. So, pipe, and inside the pipe it is going. If I take a different color pen, so it is installed in a pipe, please note, always installed in a pipe, right. So, this impact hole should always in a direction opposite to the flow velocity. Flow is flowing in this direction. So, that directly it is impacting here. Okay. So, it will to be installed in a direction where this, that means I am saying like this one, if I can see the camera here like this one, you see the liquid, this is pitot tube suppose, right. So, this is our static hole, right, impact hole or stagnation point I should say. So, what will happen here, see the liquid is flowing here and hitting this position, right, and liquid is flowing over this one. So, there is a hole on this side, okay, this side there is a hole, the fluid is flowing in this direction and it is going out. Okay. So, liquid is I mean this it is impacting here. So, there is a point where the velocity of the fluid will be 0. If we consider this as a solid body, so velocity of the fluid at this point will be 0, kinetic energy will be also 0, but there is a pressure. So, out inside the pipe also, that pressures we are calling it static pressure, right, and these pressures, the pressure at this one will be the stagnation pressure. So, obviously, the stagnation pressure, since the velocity is 0, will be much higher than the static pressure, right. So, these static holes usually can be collected as it happens in the case of venturimeters, these static holes can be, this static pressure can be sensed by piezometer rings, that means it is averaging the pressures, and this impact hole or stagnation pressure can be measured by, if I just take out one hole here and take it out. So, these two will give you the differential pressures, right. This minus this pressure P1 minus P2 will give you the differential pressure. As the flow velocity increases, P1 will increase, obviously delta P will increase. What will happen? You see the delta P differential pressure so this is equal to P1 minus P2, right. So, this P1 minus P2. So, this is the pressure, differential pressure. So, this is our stagnation pressure. So, if the flow velocity increases, P1 will also increase. So, delta P also will increase, right. So, this way, so by measuring these differential pressures, I can calibrate this in terms of flow velocity, right. And if I know the area of cross sections of the tube where it is installed, that pitot tube, I can measure the volume flow rate, or if I install it on some moving body, this entire pitot tube is installed on a moving body like an aircraft. Obviously, what will happen, you know that I will measure the aircraft velocity or the velocity of any vehicles also. Only thing, the problems, we need a clean fluid, because if there is a this hole is this is a small hole you can see here, if this hole is clogged by some particles or dust, so that will give us erroneous reading, right. That is happened actually in the case of aircraft, as you know, when it goes to large, huge height. So, as you know, the Boeings and all these things, they are going very high, around 33,000 feet, 35,000 feet. At the situation, there is a ice formations at the stagnation point. Then what they do, they put a heater coil around this one, right. So, continuously is melting that ice. So, there is no question of getting erroneous reading. So, the flow can be calibrated in terms of actually measuring the differential pressures. I can measure the flow velocity or the velocity of the vehicles or aircraft on which it is installed. Let us go back to theory again, right. Now, this is the, you see this is the relation between the velocity of air versus the differential pressure, right. X axis we have plotted the velocity of air, and y axis we have plotted the differential pressure delta P, which is in Pascal, and velocity here is meter per second, and density of 1.2 kg per meter cube, and differential pressure versus velocity of air measured by a pitot tube, right. So, this is the figure. As you can see, we will do some calculation. It is non-linear in nature, you can see, okay. So, this creates a problem. Both the kinetic energy and the pressure energy will be present at the static holes, because fluid is moving at those positions, right. Assuming energy conservation and no frictional loss and no heat loss, obviously we can write P1 by rho 0 G Z1 P2 by rho plus V2 square by 2 into G Z2. You can look at very carefully, all the units of this one will be in, you see here that G is in, if I take meter per second square, right. So, G will be Z will be in meter. So, it will be meter per second whole square, this one. This also will be meter per second square, right. P2 can be, it is the pressure. So, Newton per meter square, right. So, if you simplify this one, suppose this Newton means kg, P is in Newton, right. So, it means that P is in Newton, means you will find that is a kg meter per second square. So, if you divide by rho, that is kg per meter cube, again it will be, so this P by rho you will find will be in meter per second square, right. So, it will be like this. right. So, all the units are same, units of each item will be same, because this is the, there is no velocity of the velocity at the stagnation. So, this is a stagnation part, the Bernoulli's equation we have applied at the stagnation point, this is the Bernoulli's equations applied at any other point of the fluid, right. Here P1 is the stagnation pressure, P2 is the static pressures, and Z1 is the elevations of the static, I mean stagnation point, and Z2 is the elevation of the your static point, right. If we have this line, we can go to the next slide. So, where Z1 and Z2 are the elevations of the holes above the datum line, and G is acceleration due to gravity, which is 9.81 meter per second square. And if Z1 equal to Z2, then we can simply write V equal to 2 P1 minus P2 rho. This is equation number 2. Now, whether the rho varies, let us look at that. Now, from equation 2, we can write delta P equal to, so this is delta P equal to V square into rho divided by 2, is not it? Differential pressure equal to half of rho V square. But delta P is the differential pressure P1 minus P2. So, V obviously I can see here, you can see this is the most important equation, count for all differential pressure flow meter, you can see this is V equal to, V proportional to root over delta P, right. So, delta P if you calibrate in terms of V, obviously there is a non-linear relationship, right. So, for air at 20 degree centigrade and pressure P2 of 10 to the power 5 Pascal, that means static pressures I am talking of, with rho equal to 1.2 kg per meter cube, gives delta P equal to 0.6 V square. Thus, at V equal to 10 meter per second, we have delta P equal to 60 Pascal and delta P by P2 equal to 6 into 10 to the minus 4. And at V equal to 100 meter per second, delta P equal to 6 into 10 to the power 3 Pascals and delta P by P2 into 6 into 10 to the minus 4. What does it mean? It means that when the flow velocity, the low value of delta P by P2 ratio means that for the velocity less than 100 meter per second, 100 meter per second is a quite fast, I mean quite high speed, right. That means the difference, it is extremely high speed, 100 meter per second, right. The difference in density between the air at the stagnation point and the static holes is negligible, right. The error introduced by considering the incompressible fluid is within 1%, right. Now, differential pressure transmitter is a special type of differential pressure transmitter is necessary for particularly in this case due to low differential pressure, because if the fluid is actually air gas, so the differential pressure also will be less, because as you know the differential pressure also depends on the density of the fluid, right. So, the air has a lesser density. So, due to low differential pressure, so your differential pressure also will be low. So, we need some more sensitive differential pressure sensing element, because this differential pressure first we will sense and before converting to the electrical domain, that is 4 to 20 milliampere of current domain, I need some higher pressure, higher differential pressures, right. So, I need some more sensitive, I mean this type of system which will convert this your differential pressure to some other change like capacitive change or any other change, displacement change that can be converted in the electrical current domain of 4 to 20 milliampere. So, it gives a 4 to 20, that voltage LVDT unbalanced voltage, that means the secondary voltage which is in oppositions can be converted easily to the current domain of 4 to 20 milliampere output for differential pressure. For scheme of velocity, you see everywhere it is like this one. You have seen that in the case of this LVDT, in the case of this flow measurements also, what is the minimum flow that must be prescribed, right. What is the maximum flow, that also in the process it is fixed. So, what we will do? We will accordingly we will fix our 4 to 20 milliampere. So, the calibration is most important. How will you calibrate? So, for the minimum flow velocity we must get 4 milliampere of current, for maximum flow velocity we must get a 20 milliampere of current. Accordingly our electronic circuit, that is converter which will convert, because always you know that there are many simple circuits are available for to convert this type of signals, voltage to current signals, right. So, depending on the whether you suppose I have a 0 to 10 volt, accordingly for 0 volt I want 4 milliampere, for 10 volt I want 20 milliampere. So, that type of things can be easily made, right. So, similarly here also, instead of suppose 0 volt I have a input voltage, LVDT outputs I am getting suppose 0 to 5 volt, no problem. So, if it is 0 to 5 volt, accordingly I can set my circuit some reference voltage, resistance by which I can make 4 to 20 milliampere of current, right. Now, scheme of velocity measurement is shown in figure 3. You see here that you can see here the input is velocity V, right. I have a pitot tube, I am getting a differential pressure of delta P. So, I have a dP transmitter. So, dP transmitter is basically here not capacitive, it is a LVDT based, then 4 to 20 milliampere of current is coming. So, we have a data acquisition systems and you have PC. Data acquisition system, obviously it will convert this current to the voltage domain, then it is digitizing it before feeding to the PC, where I can record the flow velocity, and if I have to take some actions, that means I have to feedback, suppose this PC output through data acquisition card again can go back to the control valve to reduce the flow. Ultimately, what is the use of this pitot tube and all these things, I have to set some. Already the prescribed that this much of oxygen will flow or this much of hydrogen will flow in the pipe. So, to set that, so I have to measure this velocity, then feed it back to the some control valve, so that by which it will either open or close to bring the flow velocity to the prescribed level, right. Now, elbow meter, with this elbow meter is a different kinds of systems. It is actually usually used in a huge installations of the pipe. Is not suitable for the small bending of pipe. So, for the large bending of the pipe. Now, in all the cases except pitot tube usually is used for the gas. You will find that there is a large differential pressure. And there is a loss, permanent loss in both in the case of orifice meter and venturi meter. In the case of orifice meter, we have seen that this loss is more. In the case of venturi meter, permanent loss is more. In the case of venturi meter, we have seen the permanent loss is less. Now, elbow meter is an instrument. It is also based on the differential pressure measurement, but that permanent pressure loss is not there. But in fact, it is there, in fact not in that way, because whenever there is a pipe bending, there is a pressure loss, as you know, head loss is there. So, utilizing that principles without having any additional loss for the installations of the meter, we can have a elbow meter. Let us look at what is that. The orifice meter, flow nozzle, dial tube and venturi meter, we have seen cause permanent pressure loss in the system. This will create the permanent pressure loss in the system, right. All this flow nozzle, dial tube, less or more. So, obviously, it will make some permanent pressure loss. You have seen that in the case of venturi meter, there is there are different types of venturi, but long, short. In the long, we have much better pressure recovery. In the short, we have less pressure recovery. In the case of orifice meter, pressure recovery is worse, right. Elbow meter does not introduce any additional losses in the system, since it simply replaces an existing elbow or pipe bending that is being used to change the direction of flow. Right. In a process, you will find that always you need these type of things, that I need some pipe bending somewhere, okay, because all pipe cannot be straight in a process. So, you will find there is pipe bending. So, in that bending we will install that meter, so that no additional loss will be there. So, elbow meter does not introduce any additional losses in the system, since it simply replaces an existing elbow or pipe bending that is being used to change the direction of flow, right. You see here the elbow meters we have, it looks like, you see that I have this is a section of pipe bending I have shown here. You see, this is a section of pipe bending, you can see here, this is a section of pipe bending, right. That means there is a pipe here, there is a pipe here, there is a continuous pipe, and there is a pipe going also here in this direction, right. So, just that pipe bending at the pipe bending I have installed this elbow meter. Fluid is flowing through the velocity V and it is coming out, going out to this velocity. And there will be only two pressure tappings there. One will be inside the pipe, another will be outside the pipe. You see what will happen, the liquid which is flowing through this pipe, outer side of the pipe, it will have much faster velocity than the pipe which is the liquid which is flowing to the inside this one, right. It is usually increases in this direction, it is maximum here, and my minimum velocity is maximum here in this direction and minimum in this. Here everywhere the flow velocity, if you take any point, the flow velocity is supposed to be same, right. But here what will happen, the liquid which is flowing very near to the pipe bending, it has much higher lower flow velocity, and here we have a higher flow velocity. According to Bernoulli's theorem, obviously what will happen, the pressure to this one will be of the liquid, I mean will be much higher compared to the pressure, because here the flow velocity will be higher, right. So we have datum point Zi and 0. From the datum level we have taken the height of the pressure tap, this is the inside pressure tap, this is the outside pressure tap. This is our basic principle of the elbow meter. So what the advantage, that means you see that I am not putting any restrictions inside the pipe like orifice or venturi, clear. So velocity, pressure and elevation above the datum level for pressure taps on the inside or outside surface of a 90-degree elbow can be related by the expression is that shape is 90, any bending in an industrial process is 90 degree, that is the reason we call it 90-degree elbow, can be related by the expression Ck equal to Ck multiplied by V square by 2G P naught by rho G plus Z naught minus Pi by rho G minus Zi equal to, this is the equation number 3, right, where Ck is the coefficient that depends on the geometry basically of the elbow, that means shape and size of the elbow. A normal of Ck range from 1.3 to 3.2. Units you see here, if I go back, so Ck V square by 2G, Ck V square by 2G, P naught by rho G, 0, Pi rho G. So all these units let us look at. P is in Newton per meter square, rho is kg per meter cube, and G is meter per second square. So all the units, all the heads are in meter, you can look at. So P by rho G is in meter and Z is meter, so all are coming in meter, right. So volume flow rate will be expressed as Q equal to AV, A upon root over Ck 2G P naught by rho G plus Z naught minus Pi by rho G minus Zi C into A. We have combined, instead of writing A and root over Ck, we write C into A, 2G P naught by rho G plus J naught minus Pi upon rho G minus Zi, equation number 4, right, where A is the, this should be where, please note, where A is the area of cross section of pipe in meter square. The value of C ranges from 0.56 to 0.88, and the primary advantage of the elbow meter is the savings of the extra pumping cost. For the huge installation, that is a good amount of saving, right. So the primary disadvantage is that of the each meter must be calibrated on the site. It is very difficult to find the flow coefficients, as you know that this value of the C ranges from, we have always given the range. So you have to install, it depends on the slide pipe bending is not exactly 90 degrees, something else may happen, suppose it is internal cross section exactly not in circular in shape. So obviously everything will change the installation, change the calibration constants or the discharge coefficient C, right, or flow coefficient C. So that creates the problem. So each and every installation, that is true for even for almost all the installations, right. Though we can suppose we have a thermocouples, we can calibrate it in the laboratory, but it is better to calibrate at the site itself. The primary disadvantage is that each meter must be calibrated on the site, right. So the low operating cost can usually justify the calibration cost. The low operating cost can usually justify the calibration cost. The anemometer again that restrictions, so the upstream flow restrictions and the downstream flow restrictions, that means obstructions, that means any pipe bending, these that will be there. So that restriction is there, which we had previously in the case of orifice and venturi. The anemometer requires a minimum of 20 to 30 pipe diameters of unobstructed upstream flow to reduce the turbulence and swirl for accurate measurement. Otherwise, the flow straighteners are to be installed to stabilize the flow, as it is used in the case of orifice meter. It is a bundle of tubes all welded inside and put inside the pipe. So, the liquid will be, so it will eliminate all the turbulence or reduce the turbulence and wear swirl, right. Now, rotometer is slightly different. It's a meter. It basically depends on the is a variable area flow meter first of all. So, with this we are finishing these differential pressure meters. We are starting now rotometers. Rotometer, you see the basic principle is widely used for meter for flow rate indications. It is not is for transmitting instruments, or rather monitor. It is basically a monitoring instrument, but you will find this meter is extensively used for many crucial applications or vital applications like biomedical applications also, and also in the process you will find these are in plenty, right. But basically it is a, so far if the indicating instrument is concerned, I think rotometer has the only choice. If you look at the flow meters, we have several flow meters, transmitting facilities and all these things, but if I want to make a simple indicating type of instrument or monitoring type of instrument, rotometer is the only choice. Please note that. The meter consists of a float or bob. Bob is typically called in the industry, people call it ball, I do not know why. Anyway, within a vertical or transparent tube tapered to an increasing cross section area at the outlet. It must be tapered. Okay, if it does not taper, that is not a rotometer. So, the meter consists, I will repeat, the meter consists of a float or bob typically called by the engineer in the process within a vertical transparent tube tapered to an increasing cross section area of the outlet, right. The fluid entering through the bottom passes over the float, which is free to move only in the vertical directions. The float can move only in the vertical directions, right. That is the problem. Rotometer always needs to be installed in the vertical direction, right. The rotometer is always installed in the upright positions or in vertical directions. When the fluid is flowing through the meter, the three forces are acting on the bob. These are, let us look at the rotometer now. You see, this is our rotometers, right. I have a, can I take, yes. See the flowing, the liquid is flowing through these directions and liquid is flowing out these directions. So, it is to be always installed in these directions, vertical direction, right. There is a graduated scale. All rotometer is accompanied by a graduated scale. You see this tapering so small that it is very difficult to, if you look at the rotometers, it is like very difficult. It is usually its size is like this pen, most of the rotometer will find. It is like this pen, the size is very small, it is not that very huge in size, you will find this size, right, and it is slowly increased in taper, angle is slowly. So, bottom it is a smaller angle, included angle, so it is slowly increasing, right. So, that means it is increasing here, slowly it is increasing in this direction. But this tapering so small that is with the naked eye it is very difficult to visualize, because this rotometer, since it is made of hard glass or strong glass, what they do, you will find it puts on a casing also. On the back side it is getting only some front side you can see, right. That we have seen in the case of in our first lesson 1 we have shown some rotometer. So, liquid is coming in this direction, there is through pipe it is coming in this direction, it is going up, then it is moving in this direction. Again I will tell, liquid is flowing in this direction, it is going inside the pipe, inside the rotometer, liquid is flowing through this, then it is going out, right, and the float is moving inside the pipe. Float can only move in these vertical directions, right. Float can, when the flow increases, the float will move like this one, when the flow decreases, float will come down here, and it will totally fit the inside diameter of the pipe. The float is designed like that, it will fit the inside diameter of the pipe, right. There are different shape of the float that will be discussed later on. So, three forces you see, the three forces are acting on the rotameter. What are those forces? Weight of the system, okay, mass of the system, buoyancy force and drag force. Now, weight of the system, that will act downward, and buoyancy and the drag force will act upward, right. So, this Fw will always balanced by Fd and Fb, that Fw equal to Fb plus Fd, that is always. So, rotameter you can see this is basically an auto balancing system, because you see this Fw and Fb will remain constant, because that is the weight and the buoyancy of a liquid. If the liquid is same, that means same type of liquid is flowing through the pipe, it does not matter what is the velocity, density will remain same. If the density is remain same, density of the fluid remains same, your buoyancy force this also will remain same, and since we are not changing the bob, that Fw also will remain same. So, Fb plus Fw will be equal to Fd, then Fd also should remain same. That is the main interesting point in rotameters. Rotameter is basically it is auto balancing systems. If you look at it, it's very interesting part. This is auto balancing systems, right? Let us look at that. Principle of operations, how it works. For a given flow rate, the float remains stationary when the weight of the float is balanced by the buoyancy and the drag force. Buoyancy and drag force will act upward, because flow of the liquid is always from the lower to like flow of the liquid is always like this one. That means I have a rotameter here. So, flow of the liquid is always in this direction, right, buoyancy and the drag force. So, the float will act downward, Fb, that is we have seen already Fb, weight, and Fd and Fb balance, like this one. It is auto balancing system, that is you must note. Why I am calling it auto balancing system, so it will be clear from the subsequent points. The annular area between the float and the vertical tube varies continuously with the vertical displacement of the float or bob. How this annular area is changing? Yes, obviously it will change. You see, look at, let me take a white page. You see, rotameter looks like this. Let me take a different color pen. Let me take another one. So, we have a rotameter here. If I look from the top, what will happen? It will look like this. You see here, the liquid is flowing through this. So, what is this annular area? As you move up, what will happen? The area of cross section, if you find, leaving this one, will increase. Area of cross section will remain, I mean it is always increasing as you go up, right, as you go up in area of cross section increasing. Area of cross section of the float is also same. So, the annular area, that means if I look at here, annular area which is the shaded area will change as this float goes up. That means I am telling that the area of annular area at the position of the float, if I think of the annular area at the position of the float, that will increase if the float goes up, isn't it? If the float comes in, it is annual area will be no more. So, at that time what will happen? Float will just fit on this one. In that case, it will, there is no annual area. So, at the flows, this float goes up, the annual area increasing and increasing, right. These principles we are discussing. Clear? We are. So, the annular area between the float and the vertical tube varies continuously with the vertical displacement of the float or bob, right. For a particular liquid, the weight of the float, as I told you, the weight of for a particular liquid, weight of the float is constant, buoyancy force is also constant. Therefore, the drag force is to be maintained as a constant level. Drag force must be constant also. For a particular liquid, the weight of the float and the buoyancy force are constant. Therefore, the drag force is to be maintained at a constant level, right. since the area of cross section of the float is constant, the pressure drop across it should be constant. Since the area of the cross section of the float is constant, the pressure drop across it should be constant, right. This is a key point. Now, when the float is in particular position for a flow rate, the differential pressure varies with the square of the flow rate. Clear? When the float is in a particular position for a flow rate, the differential pressure varies. What is the differential pressure? Across the flow, across the float, differential pressure across the float. When the float is in particular position a flow rate, for a flow rate, the differential pressure varies with the square of the flow rate, right. So, now therefore, to keep this differential pressure constant for some other flow rate, so when the differential pressure must be constant, otherwise the drag force will not be constant. Drag force must be constant because it is equal to Fw plus Fd, Fw plus Fw equal to Fd plus F buoyancy. Weight must be counterbalanced by the buoyancy and the drag force. So, drag force must be constant. So, to keep, since the differential pressure is constant, so obviously what will happen, the area of the annual area must change. That means the float must move up and down, right. Therefore, to keep the differential pressure constant for some other flow rate, the annual area in between the float and the vertical tube must change. Must change means if the differential pressure, as the flow increases, differential pressure is constant. So, to keep the drag force constant, what will happen? The flow area must change, right. Right. Now, the variable area is provided by this vertical tube. This variable area, as I told you in the earlier, you see between the float annual area, that is if you do not make taper, then there is this type of thing will not be achieved. So, the position of the float can be made essentially linear with the flow rate by making the area of cross section of the tube vary linearly with the vertical height, right. Considering the incompressible flow, the volume flow rate is expressed as, this is the equation, CD equal to AT minus AB, 2 GB, VB, rho B, rho F, AB, rho F, AT, AB. So, let us look at what are those. So, the flow coefficient or the discharge coefficient, AT is the area of the tube, area of cross section of the tube, area of cross section of the float, bob or float, whatever, area of cross section of the tube, area of cross section of the float, area of cross section of the tube. This is the volume of the bob, okay. This is the density of the material of the bob, this is the density of the fluid, this is the area of the bob, and this is the density of the fluid. Okay, we have written all this in the all the legends are given in the next slide. Let us look at where K is the volume flow rate in meter cube per second. Then CD is the discharge coefficients, AT is the area of cross section of the tube in meter square, AB is the area of cross section of the float or the bob in meter square, VB is the volume of the float in meter cube, rho B is the density of the float of the material, it is kg per meter cube, rho F is the density of the flowing fluid in kg per meter cube. Okay. Now, if we assume that there is no variation of the discharge coefficient with the float position, we assume the discharge coefficient does not changes with the float position, which changes obviously. And if we assume that AT minus AB square by 2 is much less than 1, if I go to the previous slide, it is more clear. Okay. I am assuming that the CD is constant, okay, and this portion, that is AT minus these portions, that means I am talking of this portion, this AT minus AB by AT whole square is much less than 1, then okay, so AT minus AB less than, the equation 5 can be simplified to Q equal to K AT minus AB, because all that items simply constant, is not it in that equation. So, the volumetric flow rate equal to K AT minus AB, where K is equal to CD root over under the square root 2g volume of the bulb Vb rho b minus rho f upon AB into rho f, right. This is our constant K. So, now if the cross sectional area of the vertical tube varies linearly with the float position, if we vary the cross section of the tube in such a way it varies linearly with the with the float position, then I can write the volume flow rate equal to Q equal to K1 plus K2x, okay, to constant and x. X is the position of the float, right, position of the bob, right. So, the rotameter usually has an accurate range of 10:1, that is better than the square root sensor. So, that is quite obvious. So, the square root sensor much better than the square root sensor. Square root sensors we have seen that the 25% less than 25% of the maximum full scale range, the error is, this reading is very much erroneous. That is not the case in the case of rotameter, right. Now, shape of the rotameter. So, what we will see that in the case previous, you will find that we have seen also that if I take a different color. So, we have seen that it is tapered like this one, okay. The float is moving like this one, so it is in a casing, okay, and it is a graduated scale is there, right. So, this is liter per minute or liter per second, whatever the way you like, actually represented, right. So, this is the float. So, this is calibrated in the volumetric flow rate or velocity. So, it is a volumetric flow rate, it is calibrated. So, whenever by looking at the position of the bob, I can, if I look at here, I can tell that what is the flow velocity, right. So, this is very important in the case of rotameter. So, it is basically used for the monitoring instruments or indicating instrument, but not for transmission instrument, right. But that does not necessarily mean that its accuracy is poor. Accuracy is quite good in the case of rotameter, as I told you, and you will find that it is extensively used in the case of anesthesia. As you know that when the patients under operation, first they put an injection, physicians, for to go the patient under, they say that the patient will go to some subconscious state, right. To maintain that state, they must have continuously supplied gas, so that the patient will remain. So, to how much gas they will put to the patient knows. So, that will be they measure by the flow meter, the rotameter, and there the float, let me go back again, I am sorry. Shape of the rotameter, you will find that the float is actually they are using some light heavy plastic sort of thing. So, by looking at the position of the float, I can tell how much gas is I am giving to the patient. That because this is very important. Those who do the anesthesia, for they actually looking at and determining that regulating the valve, they are controlling the how much liquid is flowing, how much fluid is going to the patient, right. Now, floats with sharp edges are less sensitive to fluid viscosity that changes with temperature, right. So, you will find that because viscosity of the liquid, as you know, it changes with temperature, right. So, but if I make the float with the sharp edges, that will be almost independent of viscosity, right. Vertical tube of the rotameter is made of glass to make it a monitoring instrument. Rotameters are used in applications, so the accuracy is not a prime concern, but it is not that inaccurate also, otherwise it cannot be used in biomedical application, such like very crucial when the because if you give more gas to the patient, so a patient will die, and if you and if you reduce the supply of gas to the patient, so what will happen? Patient will come out of the subconscious state. Physicians cannot operate. So, till the operation is complete, the patients will be under that state. Now, here now we will solve one problems on the Venturi meter. You see here the problem looks like this. A Venturi meter is to be used to measure the flow rate of water in a pipe of diameter d, equal to 0.2 meter. The maximum flow rate is 2136 meter cube per minute. Venturis with throat diameters of 0.10 meter, 0.12 meter and 0.14 meters are available. Choose the most suitable venturi meter assuming the differential pressure at maximum flow is 918 kg per meter cube, and calculate the accurate value of the differential pressure developed across the chosen venturi at maximum flow rate, right. This is our. Now, we have given some chart also. Here see table for orifice plate. This is beta equal to, we have seen that some chart for Renault numbers, how much the flow coefficient changes. So, table for venturi also we have given, this is the pipe and throat diameters for the different Renault numbers, how the discharge coefficient changes, okay, that is we have given. These are tables are necessary for solving the problems of the venturi meter and orifice meter, right. This is one other chart we have given, last chart we have given, that is the Renault numbers, how the beta changes, table for orifice plate of 0.05 millimeter, that is the dimensions of the orifice. So, you find that how much the Renault number changes, right. So, let us solve the problem. Here you see the problem is like this one. Here CD, we can see for CD is equal to 0.1, okay, is not it? Yeah. For sorry, let me take new page. So, rho equal to 1000 kg per meter cube. So, from that if I apply our venturi meters formula, we will find that Q equal to, I am getting 340 meter cube per second. Now, here I am taking that D equal to 0.01 meter, for which CD is coming from the chart 0.988. Okay, venturi meter always you know the flow coefficients is very high, right. Then we can find for D equal to 0.12 meter, we have calculated from the formula that CD will come 0.987. So, the Q2, this is the Q1 if I assume, the Q2 will be equal to 507.6 meter cube per second, right. So, if I take a new page, now for D equal to 0.14 meter, we will find CD equal to 0.985 meter, 0.985. So, Q3 equal to 737 meter cube per second. So, we can see that the the orifice meter with 0.10 meter diameter is the best choice, right, because that is the most close one. And in this case, for this type of situations, in the case we can calculate that the delta P max, if I apply this again, this our main formula. So, now we will apply this one 0.20, that means it will be, you will find if you take a new page, it will be like this one. So, it will be 3.56 into 10 to the power 4, 0.988 by 0.968, you will find. So, you will put the all other pi 25 root over 2 delta P G, you will find that the delta P max will be 1006.1 kg per meter square, right. So, this is our equation, right. So, this is, so best choice is 0.10 meter and delta P max will be 1006.1 kg per meter square. This ends the lesson 13. Thank you.